Oops. Just need to dim the lights and stuff. Can't reach the console properly.
Sorry, do you want me to?
Yeah, no, I can reach now. It's just I need to go large. Yeah, I'll just give me one moment. But yeah. Oh, yeah. No, I haven't killed anything. That's good. Just give me one moment. I'm just gonna dim the lights more. Wee. Here we go. Oh, there it goes again. Doesn't matter. All right.
We good to go?
Yeah, we're good.
Okay. Okay. So, good evening, everybody. It's great to be talking to some of you that I saw on Saturday night, and some of you that I haven't met before. Let me introduce myself before I get onto the topic at hand. So my name is Geraint Lewis, and I'm a professor of astrophysics at the Sydney Institute for Astronomy, so part of the University of Sydney. My research area, so my day job is to do research in astrophysics, focuses on essentially the dark side of the universe, right? So I'm interested in finding out about dark matter, dark energy, the evolution of the universe, etc. So when we get to the end, if you can't think of any questions to do with what I've been talking about today, I'm happy to take questions on any of these particular topics. So one of the things I love to do is basically talk about cosmology, talk about physics, talk about the universe. And I've added this part because I've been told that scientists should advertise themselves, so I'm going to advertise myself. I've written a few books, which I think will make for excellent Christmas presents. Christmas is just around the corner. Just remember that every single one of these books that you buy, it reduces my mortgage by about this much. So I'm very, very, very grateful. And in more positive news, I have another book coming out in mid-2026, part of the Shortest History series, which comes out of Melbourne, and I've written a book on the shortest history of reality. So if you'd like to have an idea about what's going on, not that I really have much of a clue, this book basically tries to give us a summary of how scientists understand how reality works, which starts off kind of simple and gets kind of complicated. Now,
is your latest book all in Latin? I see the Latin at the top.
No, see, so the Latin at the top there is, they haven't found an important person to put a quote there yet. So that's a placeholder until somebody famous says something nice about the book. Okay. Oh, but I should point out, the foreword is by Derek Muller, who makes Veritasium. Look around the room. People watch Veritasium? Yes. So I know Derek very, very well, so he's written the foreword for the book. So this covers a whole bunch of things about a bunch of things which seem kind of obvious, but then delves into things that, when you get to the heart of it, seem very complex. And in fact, that's going to be the topic of the talk tonight, right? It's the nature of time across the universe. So, time. I mean, we all know what time is, right? I mean, time is the thing that we never have enough of, right? It's always the thing that, wake up in the morning, we do our day, we go to sleep at night, it just ticks away regularly, etc. So we all have this idea of what time is. But I get, people approaching me as a physicist and asking me, what is time? And I'm not sure what I'm supposed to say as an answer, okay? Because when you think about it, what is it that we're actually talking about? Now, this is not a new problem. So I'll just pop up a quote here from St. Augustine of Hippo, written in the 4th century. What then is time? Provided no one asks me, I know. We all know what time is. But if I want to explain it to an inquirer, I do not know. And this is the problem that I have as a physicist, trying to explain to people, what is time? So today I'm not going to be able to tell you what time is, right? And I'm not even sure what answer would satisfy you. But I'm going to tell you about how we understand how time works. So that aspect we can get our teeth into. We can talk about time across the universe. So there are two important players that we have to deal with in this story. The first one is from the 1600s. And this, of course, is Sir Isaac Newton. So Sir Isaac Newton was, the first scientist, air quotes, there's no definite definition. But he is the person, Galileo around the same time as well, he is the person that laid down the ground rules for how we approach science. And what I mean by that is that he realized that if you want to describe something in science, okay, especially in physics, what you're talking about is mathematics. You want mathematical rules. The name of the game is to basically gather some observations and be able to use those observations to make predictions into the future. How do I make those predictions? Well, I try and understand the equations that govern what's going on, and then I can use that to say what I'm going to find out in the future. Okay? And we all know this sort of thing. I don't have a ball, but if I have a ball, etc., and I let it go, well, we all know that it's going to fall to the floor. But a physicist would ask, well, how is it going to fall to the floor? Is it falling at uniform speed? Is it accelerating, etc., etc.? And Isaac Newton, who gave us the first laws of gravity, basically said, I can give you some equations. You can calculate where the ball is going to be at certain times. And that's still the way that we do science today. Now, importantly for Newton, of course, is that we're talking about change, right? How do things change with time? So when we're calculating our motion of a ball or whatever it's going to be, a planet, the moon, we want to be able to calculate that as a function of time. And so Newton had to make some statements about time itself. And his statement is that time is an absolute thing, right? And what I mean by that is that for all people, all observers, all across the universe, you can imagine that there's one giant universal clock that ticks 1 second per second. And every other clock in the universe is synchronized to that great universal clock. So time is absolute. So that was fine. This is the way that physics worked back then. It sort of made sense. If you have a couple of people with their watches and they look at the time and they go off and do stuff and they come back, they compare their watches, the times are the same. And I think a lot of people still think that that's really the way that time operates, right? It's just this thing that ticks off in the background, and our lives are just governed by this universal clock. But this all changed at the start of the 1900s. And it was this guy, right? So 2 players in the story, Isaac Newton, that gave us absolute time, and then Albert Einstein, who destroyed absolute time. So Albert Einstein, back in 1905, wrote down what's known as the special theory of relativity, okay? Now, at this time, people thought that physics was basically done, that we understood everything. But in a few short years, all of the physics that we had learned through the 1800s was essentially upended with the discovery of relativity and quantum mechanics. So quantum mechanics, of course, is the physics of the very small. It's the thing that makes your mobile phone work. It definitely is the way the universe is on the small scale. Relativity, though, tells you about space and time itself. And one of the central ideas in Einstein's special theory of relativity is that all observers will measure the speed of light to be exactly the same, 300,000 kilometers per second. Okay? Now, if you think about it, that's a slightly strange statement. Because if I pick something else, imagine I pick a train that's trundling along the tracks. I'm not sure how fast your trains move in New Zealand. They move really slow in Australia. But we can imagine a train trundling along the tracks. Okay? If I'm standing next to the tracks, I can talk about that train trundling past at 20 kilometers per hour, typical Sydney train, 20 kilometers per hour going past. It has a speed relative to me. But if I'm a passenger on board that train, and I ask how fast is the train moving relative to me, well, it's not moving at all. I'm on board the train. It is stationary with respect to me. So these 2 different observers get 2 different answers for how fast is the train moving. Yet Einstein demanded that everyone measures the speed of light to be the same, irrespective of how they're moving. Now, I don't have time to go into why he came up with that statement, but it's a pretty deep statement about how he got there. But he realized that something else has to give. If you are going to demand that everybody measures the speed of light to be the same, then something has to bend, something has to change. And if you think about what speed is, it's distance divided by time, then you're going to have to bend space and time to make sure that the answer that comes out, the same speed of light for everybody, is the same. So with a special theory of relativity, Einstein basically said the rate at which time passes is dependent upon what the observers are doing, right? This notion that there's this great universal clock that ticks away and everybody's clock is synchronized to that goes out the window. Now everybody has their own clock which is tied to them and what they're doing. So in special relativity, it was to do with motion. In general relativity, which came 10 years later, it was also to do with where you are in a gravitational field. That a clock deep within a gravitational field, i.e. close to the surface of the Earth, ticks differently to a clock in space where gravity is weaker. And it's kind of a slightly bizarre thing to think about, right? That clocks tick differently. It's not our everyday experience that clocks tick differently, right? There are already some weird consequences, which the most famous one you possibly heard of. This is what's known as the twin paradox. So the twin paradox was devised around, again, about 1905. And it basically says, imagine that you've got two twins, right? Identical twins, exactly the same age. And what we're going to do is we're going to run an experiment. We're going to take our twins and fire one of the twins off into space. The other we're going to leave here on Earth. The one we're going to fire off into space travels at very high speed, turns around and comes back again, right? So we send them off on their journey. Okay, off they go. And then they come back. And if we live in Newton's universe, where all clocks tick the same, you'd expect that when this spacecraft lands, these two twins should be exactly the same age, right? To Newton, all clocks tick exactly the same. But to Einstein, what you get is that the twin that stayed at home is older than the twin that went away on the journey and came back again. Okay? Now, again, you might say, well, this sounds like madness, but physicists have done experiments to measure this. You can measure the change in time by having different motions. And we do this all the time, actually, like at the Large Hadron Collider, where we send particles around at almost the speed of light. We can measure their lifetimes, and we find out that they're just like this twin experiment. The time for the particles going round is different to the time for a particle that just sits there all on its own. So I also mentioned, okay, so that's to do with motion. The notion that when we change our gravity, that also can influence our clocks. This can have a very noticeable effect. Again, when I say noticeable, I don't mean like to you. You will not see it, but you rely on this, and you probably don't realize it, okay? So, okay, let's do a quick test. Who's got one of these portals to hell in their pocket? All right? Virtually all of us. Who uses Google Maps, right, to get you somewhere, right? Isn't Google Maps great? It gets you where you want to go, right? So Google Maps relies on a whole bunch of things, but of course one of the things it relies on is the GPS system, right? Global Positioning Satellite System. And the GPS system is a bunch of satellites orbiting in space, and all you do to work out where you are is you get signals from those GPS satellites, and you do basically triangulation, right? You are comparing the clock in your, sorry, I have to do my watch again. We don't have watches anymore. A clock on your phone compared to clocks ticking in the satellites. Now, those clocks in the satellite, well, they're different to your clock. Number one, they're moving at around 20 to 30 kilometers per second. Number two, they're a few hundred kilometers up. So gravity up there is slightly weaker than gravity down here. Okay? So it turns out that the GPS system has to account for Einstein's theories of relativity. Okay? They have to correct for the fact that the clocks ticking in orbit are ticking at a different rate to clocks ticking on the Earth. Okay? Now, I was told a story, and I do not know if this is true, and I do not remember who told me the story, but does anyone know what GPS was invented for? Military, to do what? It wasn't actually quite for navigation. It is navigation, but of particular things. Ballistic missiles. So the issue was this, right? You may have heard that in the 60s and 70s, there was an arms war going on, and the USSR, or the Soviet Union, and the Americans were building lots of nuclear weapons, and everyone realized that if you put nuclear weapons where they're all together, then somebody has to just drop one nuclear weapon onto your stockpile, they're all gone. So what do? You go and put them in silos, and you make those silos very, very reinforced. How reinforced? Well, if a nuclear weapon goes off 100 meters away, your silo will still survive, okay? So the question was, well, how are we going to get our nuclear weapons on top of the Russian silos and get them to miss ours? And it was by developing this entire system of GPS. It was so you could plonk a missile directly on top of another missile. So that's what they did. And the scientists said to them, we can build this system of satellites, but you know that crazy German scientist who died in the 50s, right? We have to correct for the bending of space and time, right, as part of this. And the generals went, no, that's mad. Clocks just tick at the same rate. So to test GPS, apparently the test for GPS was that it was an aircraft carrier, and they had to drive themselves into San Francisco Bay with the curtains closed so they couldn't see where they were going, and they were just going to guide themselves with GPS, okay? So the military insisted that there was an option that they could turn off the relativistic correction when they realized that the German scientist was talking nonsense, right? It turns out that when you turn it off, okay, GPS becomes useless within 2 minutes, okay? So the differences, which are now millionths of a second in clock times, if you want to place yourself within 1 meter or 10 meters or 100 meters, okay, if you turn off that correction, very quickly GPS becomes utterly useless. So every day when we use Google Maps, etc., we are relying on the fact that we have to correct for these effects of relativity. It's really there. So what we have to do, what we want to do in this talk is that we firstly realize that we have this notion of time which is malleable, right? Time is not a constant thing. Time sort of changes depending upon what's going on. And what we want to do is try and understand how does time work across the universe. And to understand that, we've got to first try and understand how the universe works. So I showed this picture on Saturday, but let's pop it up again. So this is all of modern cosmology in one picture, okay? So as I mentioned again on Saturday, our modern understanding of the universe is almost 100 years old. It's going to be 100 years old by the end of this decade. So it was the end of the 1920s when we got the theory from Einstein and Friedman and Lemaitre and the observations from Hubble and Slipher, which allowed us to piece together the modern picture. And the modern picture is, of course, is that we live in an expanding universe, okay? And that expanding universe, what that means is that our universe hasn't been around forever, okay? So things are expanding apart. If we wind the clock backwards, we wind them closer and closer together. There must have been an initial moment to the universe, okay? So in this kind of picture, we get this start point, which is the Big Bang, and this was the day without a yesterday, okay? So there was, but what happens before there, we do not know, right? But this is the start of the universe. The universe was hot and dense, and it was a soup of like energetic particles. But as the universe expands and stuff cools down, then matter can come together. You start to form stars. You start to form galaxies. And you come along to basically where we are today. So one of these little blobs here is meant to represent our Milky Way. And the thing that we discovered in the last 25 years, which has changed the picture, is that if you look at this picture we've got here, birth of the universe. Universe is roughly 14 billion years old, and about 5 billion years ago, the expansion of the universe, which was slowing down, is now starting to speed up. And this was due to the discovery of what's known as dark energy, this dominant stuff in the universe. So we've got a good picture of how the universe has behaved, okay? And the key thing is that expansion means that the universe of yesterday is different to the universe today. Okay, things were closer together, and if you want to think about it, it means that the gravity of the universe was different yesterday to the gravity in the universe today. So our universe is changing over time. So as an astronomer, the question I have is, well, how does this expansion influence the way I observe the universe? Okay, so if we think about it, if you imagine that this is the Milky Way galaxy today, and we're observing the universe. Okay, so we're looking out into the universe, and we're collecting light in our telescopes, but that light has traveled over some time to get to us. So as you know that when we look at the sun, we see it as it was 8 minutes ago. We look at the Andromeda galaxy, we see it as it was 2 million years ago, before the first modern human walked upon the Earth. I regularly observe galaxies that the light that we see set out before the Earth even existed. Right? The Earth's only been around for 4.5 billion years. I collect light from 10 billion years away. So we look back into the universe and we're collecting light from this time when the universe was different. So the question is, what's the effect of that? All right, so this is the kind of picture that we have, okay? So again, what we've got inside that top part there, this is our expanding universe. So up there, 13.7 billion years ago, we have the Big Bang, then you've got all stuff being close together, and then it moves apart, okay? When we collect the light that we see from these distant galaxies, as I mentioned, that light has traveled across this expanding universe. And one of the things that happens due to the expansion is that light gets stretched. Now, I'm going to do air quotes around the word stretch, because if my students were here, they would say, no, it doesn't get stretched. It's more complicated than that. The answer is yes, it's more complicated than that, but you can think of it as light stretching. And what does that mean? So if you take a light ray and you ask what is its characteristics, the most important characteristic is its wavelength. So long wavelength light is red, short wavelength light is blue. And so if you start off with blue light that gets emitted between two galaxies, due to it traveling across the universe, it appears red, okay? And of course, astronomers give this the really unimaginative name of redshifting. This is what's happening. The light is being stretched to longer wavelengths. But it turns out that this also has another effect. And that other effect is that when we look back over the universe, this redshifting should mean that we get to see the universe running in slow motion, right? In a similar way that I could talk about the clocks running more slowly deep in a gravitational field compared to up in space. I can talk about clocks running more slowly deep in the past of the universe compared to the universe today. So let me just pop up, of course, the person that led us down this path. So again, I showed this picture on Saturday. This, of course, is Edwin Hubble. I know that says 1929 at the bottom. This is not Hubble in 1929. He was a younger man in 1929. This is when he was a bit older. So it was Hubble who did the first observations that basically revealed that, that distant galaxies show this redshifting, that they appear to be moving with respect to us because the light looks stretched. You get a Doppler shift out of it. And it's from his observations that we now understand that we live in an expanding universe. Okay, but the flip side, as I mentioned, okay, is that the consequence of the fact that we're looking back into the universe is that we should see clocks in the universe. If I could see a distant clock, I should see it ticking slowly compared to a clock with me today. Now, that's kind of interesting, but as you probably know, when you look through your telescope, you tend not to see many clocks out there, right? And this is because the universe just loves playing with our minds and making everything we want to do complicated. So the question is that if we don't have a clock where we can see a hand moving, what do we use to time time in the universe? And in fact, the answer was realized very quickly, okay? So let me just do this part first. So again, if you imagine I'm looking back out into the universe, this is us today, looking back 2 billion light years, 4 billion light years, 6 billion, all the way back towards the Big Bang over here. Then I can predict how big my slowing down is going to be. All of the nearby stuff that goes on, that basically looks like the universe around us today. I shouldn't expect to see any slowing down. But if I can see back, say, 8 billion years, then all clocks should be running by a factor of 2 slower. If I can push back to 10 billion years, they'll be running a third of the speed that we have today. And the further and further back that I can push this, the slower and slower all those clocks will appear to tick. But what do I use as a clock, right? And in fact, the answer was realized very quickly, okay? Just only a decade after Hubble did his work, there was this paper published August 31st, 1939. Does anyone remember what happened on September the 1st, 1939?
Don't mention the war.
Don't mention the war. That's right. Germany invaded Poland. So this paper came out of the Mount Wilson Observatory and by Wilson himself. And Wilson basically said, oh, I know what we can use as a clock. What we can use as a clock is exploding stars, right? Stars, right, they vary in brightness. They get brighter and they fade. And so if I can use that brightening and fading as a clock, I'll be able to basically use that to measure how slow things are going in the distant universe. I imagine I see something brighten and fade over a week in the nearby universe. When I look out 5 billion light years, it'll take 2 weeks to do the same thing. So it's a great idea. 1939, just remember that. See how quickly they solved this particular problem, right? So we need stars that explode, right? So we need supernova, right? Wide supernova, because they're the biggest explosions that we have. But we have a problem, okay? The problem is a couple of things. So number one is this picture here captures the lives of stars. So I don't know if you know how many different kinds of stars there are. You know, lots of people learn, you know, the various acronyms from O stars down to brown dwarfs. So these are the range of stars that we get, okay? So brown dwarfs are the smallest stars, blue supergiants are the largest stars. Can anyone tell me what is really wrong with this picture? I'll give you a clue. It's to do with this star here. What color is the sun? White. Why do they always draw it yellow? Does anyone know? I am convinced that we draw the sun as yellow because when we're in kindergarten, the kindergarten teacher tells us, draw the sun, you draw it yellow, right? The sun isn't yellow, the sun is white, right? So these are all the kinds of stars that are out there, and we want to find stars that we can see across the universe. All these stars down here, which are low mass, they're pretty pointless because they live their lives, they live long lives, and they run out of nuclear fuel and they just switch off. Stars like the sun, they'll become quite bright, they'll become red giant stars. but they become planetary nebula, and planetary nebula aren't that bright, so they're no good. So what we want actually is we need to move up into the more massive stars, okay, because they explode violently, right? So they produce really bright explosions. The problem that we have, of course, is that there are different kinds of stars, and so we would expect there to be different kinds of explosions. So more massive stars explode one way, less massive stars explode another way. But I'm just going to tell you why supernovae are so important. I'm not sure how much you know about supernova, but this is one of my favorite pictures of a supernova. So here we have a spiral galaxy, okay? Spiral galaxy probably home to, let's say, 300 billion stars, okay? Now, one star in this galaxy, this one here, exploded as a supernova. So it was a giant star. It came to the end of its life. It ran out of nuclear fuel, collapsed, exploded, and blew itself apart. And for a period of around 2 to 3 weeks, this one star will emit more light than those hundreds of billions of stars put together. Okay, that's how bright a supernova is. Okay? That makes them really good because it means we can see them a long way out into the universe. We can see them back over billions of years. So the big problem that we have, though, is that the stars, okay, this one here, it'll have its own peculiarities to do with its explosion. Okay? How massive it was, what was the chemical elements in its atmosphere, that dictates how it explodes. But people realized, okay, that if we take this kind of supernova, okay, and find supernova like it, okay, so you try and find explosions which are similar, then you start to see that they start to show very, very similar light curves. So again, this is days across the bottom, this is brightness up the side, so there's a rapid increase in brightness, and then there's a fade in away. So these are all nearby supernovas, so they're all doing basically the same thing. So these can be our clocks, right? And these can be our clocks. We can time how long things are taking in the universe by, oh, I just realized why the words are missing there, sorry. On a yellow sun, I will point out. We'll get this brightening and fading, so we can basically use this time scale to measure how time is passing. We just need to find more of these explosions out there in the universe. So, oh, sun's go to bed. So this all started to change in the 1990s. And it was the launch of the Hubble Space Telescope that did it, right? Hubble Space Telescope, 2.5 meters in space, not a particularly big mirror anymore, but above the atmosphere, it could see really, really deeply, right? And there was a number of projects underway. And one of them was called the Cosmological Supernova Project. And the goal of this project was to measure the expansion of the universe. That was its goal. And as I mentioned on Saturday, this had been something that had been argued about for 50 years. And so again, we don't need to worry about the details of what's going on in this picture, other than across the bottom here, we have redshift. And so this is essentially telling us how much light is being stretched, i.e. we're seeing light from further and further away in the universe. This is nearby, this is far away. On this side, we've got the brightness of the supernova in magnitudes, and I still hate magnitudes to this day, but let's not worry about that. And we have our data up there. So these are the brightnesses of supernova, okay? Not all supernova, but they focus on a particular class of supernova. One's called a supernova 1A. Why? Because out of all of the explosions that they looked at, these seem to be the ones that seem to be the most identical for each explosion. And they're thought to occur about where you have a big star and a little star, and the big star loses mass to the little star, it goes past a critical point, this star explodes, okay? So what they were doing is they were trying to measure the expansion of the universe. They accidentally discovered dark energy. And that won the Nobel Prize for Adam Rees, Saul Perlmutter, and Brian Schmidt back in 2011, right? So it was a big kind of result. Everyone was really excited that we had discovered this really weird stuff about the universe. But there was something else, right? So to basically make these measurements, they had to put all of these supernova on the same sort of calibration, okay? You had to make sure that you were treating each supernova exactly the same way. And one of the things that you had to do is ask the question, right? Exactly how long is it taking it to rise and how long is it taking it to fall, okay? So you were essentially getting this clock for free, right? It was part of the analysis. You had to basically time that rise and fall time. So in 2015, I've forgotten the year of this. Let's say 2015, it was something like that. They finally published this result, okay? So remember, the prediction was in 1939. By the 2010s, we had managed to do the actual measurement, okay? Now, I'm going to just say that that is not unusual in science for things to take almost a century. But let's just take a look at what we've got going on here. I'm sorry about the units that they use. They flip things over, right? So this just means things are going slower. And this is, again, looking out into the universe. This only goes back around a few billion light years. So it's not that far, okay? So here's today at 0. And up top there, you can see there's all those supernova data, and they're clustered around 1. So they're all the supernova whose light curves are doing exactly the same thing. They all take, let's say, 2 weeks to do this and do that, all of them. And then as we go out into the universe and look further and further back, you see that the supernova light curves are getting slower and slower and slower, okay? And that white line that you can see, that's the prediction that you get from Einstein's equations. So it works, right? When we look back, about 6 billion light years. When we look back over 6 billion light years, we look back all the way to the most distant supernova we can see, and it's exploding in slow motion, okay? So it takes basically 1.5 to 2 times longer than the ones that we see in the nearby universe. So I said that was done, again, I can't remember exactly what year it was, but again, it took more than 70 years for this measurement to be made. But in the less than a decade since this has been done, we have now got, instead of this handful of supernova points, we've got thousands of them. And so I'm just going to pop up the latest kind of result on this. And I'm going to just illustrate something, right? So this is a paper that was published last year. So there's 2 cool things. Number one, this is part of the DES collaboration, which is the Dark Energy Survey collaboration. So this is using the 4 meter in Chile to basically try and measure dark energy by measuring supernova. First thing to notice is how many people are now involved, right? Why are there so many people? Because it takes a factory of work to gather this data, to process the data, to analyze the data, to get the results out. But I'm kind of happy because I'm third author on this paper because I was involved in the analysis. But we now have 1,500 supernova. So instead of just a handful, and if we look at the results for this, so here's a similar kind of picture again. Here's today, this is now 1 plus Z on the bottom. Here's today. Here's the light curve width, which is a better unit to use. If we lived in a Newtonian universe where time was a constant, then all the supernovae should lie along a line which is equal to 1. But you can see here that as we go to more and more distant supernova, they're getting slower and slower and slower. Okay, so everyone happy with that? The time runs more slowly in the universe? People not convinced?
The question I have is, what's the reason for the wild variation of the error bars?
Oh, there's not wild variation in the error bars. The error bars are actually very, very well behaved. What this tells you is that the measurements are hard. So the error bars are big because the measurements are hard, which is why we need 1,500 of them to get such a good trend. What we would love is for all the error bars to be tiny, 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 but 30-meter telescope is still a few years off. All right, that's what we need to get there. All right, so everyone's happy that time runs more slowly in the universe, right? I'm looking around the room, just checking there's no dissenters. Good, good. Because not everyone is happy, right? And why do I say that? I say that because we've looked at supernova here, but supernova are not the only variable things in the universe. Okay, so I'm just going to show you a little movie. There might be sound attached to this. I'm not sure if it'll play. Let's see what happens. Yeah. Is it going to play? There we go. Oh, don't have to worry. It's just rumbling sounds. Okay. So the other variable stuff in the universe are these objects called quasars. Okay. So quasars are supermassive black holes, many of them with a mass of hundreds of millions to billions times the mass of the sun. Okay. So that black hole is located in there. Okay. Because even though it's got all that mass, black holes are still very small. It's got an intense gravitational field. Oop, let's see if I go back and run that again. I should talk a bit faster. There we go. It's got an intense gravitational field, so it pulls in matter, and that matter swirls around at almost the speed of light, and it glows really brightly. And this volume, right, you can see here, okay, this is roughly the size of the solar system. Okay? So these are really, really bright. They can be a billion times brighter than the sun, but they're also really, really small. So when they're far away, you see them as bright dots of the sky. But you can see in this animation, there's a big jet there, there's lots of stuff going on, and that means that the brightnesses of these objects varies. Okay? And so here's an illustration of what a quasar looks like. Some of you might know this one, 3C273, which is a nearby quasar, so you can actually see some structure around it, and it's got a jet there. But lots of them, when they're far away, they just look like points. And the key thing is that they vary in brightness. Okay? So this is what you get when you look at a different 3C source between 1930 and 1950. Again, silly magnitudes up the side, but you can see that the brightness of this thing varies all over the place, up and down, up and down, up and down, because of all that stuff going on. And so what you would expect is that if you look at quasars varying in the nearby universe and quasars varying in the distant universe, you'd expect to see the ones in the distant universe varying in slow motion compared to the ones nearby. Yes? And people searched for that, and they didn't find it. Okay? And what does that result in? It results in stories like this. Okay? So, these are reasonably respectable. Well, reasonably, that's New Scientist, reasonably respectable. And this is phys.org. Stories about how astronomers have looked at these distant objects and they don't show the time dilation that they're supposed to. And of course, that leads to claims like this one. Is the Big Bang Theory wrong? Okay? And we get this one a lot, right? So the key point is that people have been looking for about 50 years for this variation, time dilation in quasars, and they just weren't seeing it. They weren't seeing it at all. This changed, though, a couple of years ago. I think it was, during COVID that I started working on this, right? So there's this telescope here. Does anyone recognize this telescope? It's the Apache Point. I think it is. Yeah, it's the refurbished Sloan. Maybe. It's in New Mexico. I know that much, right? But the Sloan Digital Sky Survey mapped the sky, and they identified quasars. And then for the last 20 years, they've been collecting data on these quasars. And just in a narrow chunk of sky, they've gone back time after time after again, and then they get these light curves, right? So you can see the variation that's going on in these light curves. And so if we just zoom in on that, again, you can basically see that they're all basically doing different kinds of things. And there's a few questions that you have to ask yourself about this, right? These quasars are different in the sense that they've got different masses. So you've got some with maybe a black hole of a few tens of millions of times the mass of the sun, some with a few billion times. Do you expect their variability to be the same? Do you expect one to be more violent than the other, etc.? But if you look at them, you see these variations. And so I was working with my colleague here in Auckland on this particular thing, and I'm just going to show you this kind of light curve, right? So do you guys recognize this kind of light curve? Does this look like a quasar light curve to you? I mean, the variability looked a little bit like the variability that we saw in the last one, or not? Nobody wants to commit. It's dark, I can't see you, and there will be no quiz at the end. Well, no, this isn't a quasar, actually. This is a stock price, right? And this is Tesla. Okay. Why am I showing you the Tesla stock price, right? Because when you look at this, the variability you see in the Tesla stock price, right? It's not random, okay? So it's not random like it's truly random, going up and down, completely random. It has trends to it, okay? And there are many market analysts who will sell you all kinds of things for identifying those trends. But this variation, a statistician would say it has the properties of what's known as a damped random walk. It has a kind of variability, but it also has a time scale written into it, okay? And what we've realized is that our quasars, as they vary, also follow basically the same kind of variations as the damped random walk that you see in stock prices. And you might say, well, that's weird, isn't it? But not, if you think about it, why do stock prices vary? Because lots of little things are going on in various places, influencing the prices. And it's the same with the quasar light curves. Lots of little things are going on and influencing the brightness. And so what we can do is we can treat them in the same way, but a time scale is like a tick of a clock, right? So if I know there's a time scale for it to do something, I can say, oh, I can use that as a tick. So as I mentioned, my colleague Brendan Brewer, who's up at Auckland Uni there, we've worked on this before. We actually went through this. I don't really have time to go into too much of the details, but essentially, because we had this big sample of quasars, we were able to group like quasars together in the same way as they used to group like supernova together, and we could get their characteristics. And essentially, the thing is that we haven't got any pretty plots because it all ends up being statistical at the end of the day. But the key thing is that the light, the variations that we see in quasar light curves and the timescales that we see, when we look at the distant universe, we do see them going slower, okay? And in fact, because quasars are much brighter than supernova, and we can see them back over 10 billion years, the ones at the most distant, their variations are going at 1/5 the speed of the ones nearby, okay? So, again, this is great. Einstein's happy because this is kind of verified the expectations that we get from his equations. So time across the universe is not rigid, right? Time across the universe is flexible, okay? That's the message that you need to take away from this. And in the last few minutes, do I still have a few minutes? I'm looking around the room. Yeah. The last few minutes, I just want to touch upon what this means because some people don't quite get the importance of this kind of statement, right? So, as I mentioned, the first thing is that I got asked an awful lot of questions. We had a press release when we we found this stuff, and I achieved my personal goal of appearing in the Daily Mail, so that was a great thing. I also appeared in New Scientist. But so the question I was asked over and over again is, does time really run slowly in the early universe? Okay, and the point that is kind of confusing is that if you were there, things would seem completely normal. Time would run at 1 second per second for you. It runs at 1 second per second for me, but I see your time running slowly. Okay? Now you might say, oh, doesn't that kind of mean that it's an optical illusion? Yeah? And you might say, well, when we did special relativity and we sent the twin off and they came back, their clocks run differently. When they came back together, they were no longer in sync. The problem I have is I can't send you to the early universe and bring you back and compare our clocks today. But this is as real an effect as the different runnings of clocks in any aspect of relativity. So my answer in general was this. I gave the following to a Chinese news story, and they printed it verbatim. And it wasn't me that said this, right? They wanted me to describe what time was. And so I said the following, right? Time is wibbly wobbly, timey-wimey stuff. It is. It's just not that rigid thing you like to think it is. It does bend. It does warp. And it does mean that, again, if I could send you to the early universe and bring you back, then our clocks wouldn't be synchronized because you were in a different gravity to me by the time you get back. These effects I mentioned are small. Okay, so on the Earth, you can calculate how big these effects are. So here we have two astronauts. They're twin brothers, Mark and Scott Kelly. And so Scott spent a year on the International Space Station, moving at 20 kilometers per second in a different gravitational field. You can calculate that after that year, when he returned to Earth and compared his time to Mark, it would only be 5 millionths of a second different, right? That's all it would be, right? The gravitational field of the Earth is weak. It doesn't have a big effect on us as humans, but GPS, as we've already said, has to be much more sensitive, right? Millionths of a second, that timescale is too long for GPS, right? You need smaller timescales for that to work. So it does exist. And of course, what we know is that we just need to consider places where gravitational fields are stronger, right? So I can build a time machine. I know exactly how to build a time machine, okay? All I need to do, engineering problem, all I need to do is find a place in the universe where gravity is really strong. And that's a black hole. We know we have a black hole in the middle of the Milky Way. It's a few million times the mass of the sun. And all I need to do is go and spend time near the black hole. When I'm near the black hole, my clock ticks at 1 second per second. Out there in the universe, your clock ticks at 1 second per second. But our clocks are not synchronized. And so I could go and sit down there for what might be, I don't know, let's call it a week for my time. The closer I get to the black hole, the bigger the effect, the more danger, right? But when I come back out, more time will have passed in the outside universe. And of course, we all know this now because it was spoiled by Christopher Nolan, right? I mean, he told everybody this in Interstellar, okay? Although the part where you go inside a black hole and you find some sort of multidimensional library, that's not in the mathematics. I think he made that part up. But this part about Cooper going off into space, and while he is in the vicinity of a supermassive black hole, his daughter Murph goes from being a young girl to an old woman, right? That's precisely what that time machine is. That's what he did. It was exaggerated for the film, of course, but the process is completely in line with time in the universe, okay? So we can build time machines to go to the future, which is kind of cool, isn't it? Yeah? No, nobody wants to go to the future? Come on, look at the present, seriously, right? Okay, but that's not what people care about. People don't want to go to the future. Well, some people want to go to the future. What people want to know is, can we go to the past? And honestly, I think it's a bad idea, because I think we would. I was thinking about this. I mean, I lived in the 1980s. If I went back to the 1980s now, I don't think I could survive. I'm trying to remember how a phone works, right? But this is the kind of question that people ask all the time, right? They say, oh, can we travel backwards in time? Now, I know I've said we can travel forwards in time, but most people say, no, it's science fiction. Traveling backwards in time, that's pure science fiction. But it's not. Okay? So, on Einstein's 70th birthday, his mathematician friend Kurt Gödel, who's famous for the incompleteness theorem, if you know your maths, basically gave him a Christmas present. And his Christmas present was a time machine. Now, being a mathematician, it wasn't a physical time machine. It was a mathematical time machine, okay? And his time machine, this is an illustration of it, it's Gödel's rotating universe. So basically says, if I take my universe and I can give my universe some spin, then I can get paths in that universe that completely come back to where they start in space and time, right? So you can go back to the origin. So in the mathematics of relativity, there's nothing to stop you building time machines to go to the past. I mean, it's an engineering issue. Can I bend space and time enough to give me that kind of path that takes me back in time? I mean, it's a big ask to basically rotate the entire universe to build a time machine. But the mathematics exists, right? So it's not ruled out. And the story that I actually like about this, and I'm going to mention this because this guy does not get mentioned enough. So this is, Gödel was not the first. So it was this guy, William van Stockham, who discovered the rotating universe in 1938 when he was working as a student in Edinburgh and then in the US. Of course, as we already mentioned, in 1939, you got the German invasion of Poland, the start of World War II, and van Stockham basically joined the Dutch Air Force in exile, and he was shot down on D-Day. So, you know, he had come up with this rotating universe independently, and he never became famous because of it. My mission is to make sure that everybody gets to know his name, right? So I'm just going to basically point out that this notion of time machines, and I'm hoping in the future time machines look like this. I think it would be great. Time machines are not impossible, okay? Time machines are not impossible. So if anyone tells you that they are, they're not. Relativity allows them. We just don't know how we would build them. There are lots of ideas though, right? You can have ideas where, I know Doctor Who comes into this, best time traveler ever. But you know, there are structures in relativity called wormholes. Again, we have the mathematics for these that allow you to build these closed paths that would allow you to travel to the past, etc. So the things aren't ruled out, right? People tell you, oh, you can't build a time machine, but there's nothing in relativity that tells you that you can't. And I'm just going to finish on the one that I think might be the one that's going to be the first that we get, is this notion of warp drives. Now again, warp drives, that sounds like science fiction, right? And we all know that you can't travel faster than the speed of light, and therefore we will never have a galactic empire. Trump would have a galactic empire, thank goodness. But again, it turns out that if you look at the mathematics of relativity, that rule about you can't go faster than light is a rigid rule, right? But like all rigid rules, you can bend it a bit. And there's this idea that if you bend space and time the right way, that light rays inside here, they'll still basically you can't go faster than light, but your spaceship can travel faster than light somewhere else moving in the universe. And in fact, this entire notion, which is known as the Alcubierre warp drive, right, which has been around since the early 1990s, has this mechanism where you compress space in front of you, expand it behind you, you can travel at any speed you want, okay? So that's what I wanted to get across to you is a couple of things. Number one is that time is not the simple thing that we like to think it is. Number two, it is bendable and stretchable, and we see it, and we've measured it, and we know that time can do this. But the consequences of this are things like time machines and warp drives, which aren't ruled out in relativity. And until they are ruled out, I'm hoping that people will still look for these solutions, right? How great would it be to travel to Alpha Centauri in no time at all? I think it would be good fun. Okay, I should probably finish there because I've gone over, and happy to take any questions. So thank you.
I have one. If you extrapolate that time dilation, from our point of view, then is time effectively frozen at the instant of the Big Bang?
Yes. But we can't see the Big Bang, so can't see that.
So obviously some physical process happened. So there must be a bit of a mismatch of that theory with what actually happened, or?
No. Well, so you're talking about the birth of the universe, which is a complicated time, right? So we don't understand that initial moment of time equals 0. But we do from the moment just after that. We can understand the history of the universe. If we could see that time, we would see it effectively frozen on the sky. It would be the equivalent to maybe you know this, if you drop someone into a black hole, I mean, not a friend, of course, but, you know, if you drop someone into a black hole and you look at them fall, okay? So they're falling, but as they get deeper and deeper into the gravitational field, the same effect comes into play, right? So you would see them slow down, and they would appear to freeze before they get to the event horizon, right? So they would freeze, and then they would fade away, right? So it's a well-known effect that when you get these points in your space-time where weird things happen, you can get this freezing. So it's not weird really that it exists, but we can't see it because we can't see past the cosmic microwave background. So we can only see 100,000 years after the Big Bang, not before.
Could you comment on the timescale model of the universe and the suggestion that it shows that dark energy isn't required?
Do you mean David Wiltshire's? Yeah. Comment on. Here we go. No. I'm just choosing the right words, right? So David's idea is that is basically all of this, right? It's that time runs differently in empty places in the universe compared to clustered places in the universe. And the fact that you have that difference means that light rays that traverse that kind of space, the influence on them makes it look like we're in an accelerating universe with dark energy. From what I have seen of that idea, I think the idea of time being different is correct. The fact that light is being influenced is correct. But I think the scale at which he says it operates is too high compared to the differences about how empty an empty region is compared to how clustered a clustered region is. So there's something going on there which doesn't quite gel with me. I would have thought that given the scales of that we have in our universe, that it would be a much gentler effect than the one that he's claiming to be there. So I'm not saying it's wrong, but what's the right way to put this? The idea hasn't yet set the world on fire, right? It's concentrated in Christchurch. Is that a bad thing to say? Looking. Okay. Okay. Yeah.
Good observational ways of testing this.
Oh yeah. Well, so this is what David and his students and postdocs are doing. Is that the issue is that you have to make it work for all of the observations that we have, right? So time dilation is one of them, the observation of the cosmic microwave background, etc. The problem that you have is that once you go down the road that David has, which is you make a lumpy universe, then your calculations become much harder. So if you imagine that when we consider our universe, which we treat as effectively smooth, then I can average over things, and it's easy to do those calculations, so people can do that. But if you wanted to ask, what is observation X in the timescape model, then you have to go, all right, I have to go all the way back and do the calculations of how I see through all these different things. And that's what they're trying to do, is they're building up that evidence about what they can explain with their theory. I said, as of yet, it has not set the world on fire. But again, I'm not saying it's wrong. I think scientists, as a scientist, you have to be very careful about pointing at something and saying it is wrong, because scientists are often wrong when they say things are wrong, right? So, it's all about what is the evidence given the observations, and that's what they're working towards at the moment.
If I've understood you correctly, and I may not have, the time dilation is affected by two things for these quasars. One is their size, because that affects the local gravity, which affects the time, and their distance because of the expansion of the universe. Or independent, or
there's a physical time scale written into the quasar to do with its mass and how big its accretion disk is and how deep its gravitational well is, etc. So if I've got a big quasar, it will have its own intrinsic time scale, and if I've got another big quasar, it should have a similar kind of time scale, and I've got a little quasar, it will have a different time scale. So those are independent. They are tied to each of those objects. The other one about the cosmological one is all about how far away they are. Now, there's no correlation between how far away an object is and us, right? So it's they are independent, right? What we had to do, and I didn't have time to go into it here, is that with the 200 quasars, we had to sort of group them together. We had to say, you're massive, you're massive, you're massive. We'll put you in a group together. You're just chubby, you're chubby, you're chubby. You can go in a group together. You're teeny weeny. We'll put you in a group together and get the time scales from those, and then add on the cosmological one on top of that. Because in that basket, so here's my basket of massive quasars, right? They're all going to be at different distances. And so each one will have a different cosmological signal, even though their intrinsic signal might be the same.
And you can work out its massiveness independent of its top time.
Yes. I'll say yes. Quasars are complicated things, right? But there's a general scaling rule, is that the brighter they are, the more massive they are. But of course, when you say the brighter they are, you're now talking about something that varies. And so what do you mean by brightness? Is it the average, or what is it? So there are diagnostics that people use. So they, again, calibrate them in the nearby universe to apply to the more distant objects. So there is a bit of flex in that, but we think we've captured much of it. I won't say most of it, but much of it. We still have higher order things we need to worry about.
If you've got photons traveling for millions of years at the speed of light, how do they experience the gravitational fields or whatever they pass through? Do they see it all happening as an instant, or do they not see it happening at all? Or how will it work?
All right. So one of the things I love about light, I love about photons, is they don't experience time at all. So to a photon, it is... So who's going to look through a telescope tonight? Anyone? Pick an object. How far away is an object? Let's say Andromeda, which you can't probably see from here, but let's say Andromeda anyway. 2 million light years away, okay? So a photon is created in an atom, in a star, in Andromeda, ching, comes into existence, okay? Travels for 2 million years, ding, arrives in my eye. If you could ask that photon, how long did that take you? It said it was instantaneous. I was born and died at exactly the same time. Right? So they have no experience of time. at all. And their paths do all kinds of wacky things as they travel to the universe, but they don't experience anything. They don't know anything about their journeys. Is that satisfying?
But it has come from a long way away. It's changed colour.
Oh, see? Oh, this... All right. All right. Light, okay. No, I have trouble with my honors class getting this point across, but I'll try. Light carries no information about itself. It doesn't have a time. It doesn't have a wavelength that it knows about, okay? So when I talk about the wavelength of light, what do I mean when I talk about that? The wavelength of light doesn't mean anything at all unless I talk about what it was when it was emitted compared to when it's received. And that involves that light interacting with observers. Okay? So the light doesn't carry information. What happens, I said, that's why I did air quotes around the photon stretches. It doesn't stretch because the photon has no size, blah, blah, blah. It also doesn't have a wavelength. But what changes is what's happening to the emitter and what's happening to the observer in terms of the universe that they're in. The universe back there was denser, here it's less dense. So it's that change that means that when I interact with that photon, I would say it's got different wavelengths. People don't like that either, I know that, but it's true. So again, if anyone wants to come to my general relativity class next year, we can go through this. But when you talk about light in terms of relativity, it has no properties. It's a null particle, and null means it carries no properties, no mass, no time, nothing. It has nothing. And you can only talk about how it interacts with observers.
Can you say that it has certain energy?
No.
Oh, really?
Well, I mean, okay. We can do this. We can do this. Right. Well, everyone knows what kinetic energy is? Yep. Yeah? No? Oh. All right. So kinetic energy is the energy of motion. Okay? And in classical mechanics, there's a formula, 1/2 mv squared, energy of motion, which means that if I take an object, right, and I lob it, and it hits something, right, you would say, oh, it's got kinetic energy, whack, it turned into something else. Kinetic energy, right? So this thing is moving, 1/2 mv squared, but if I'm running next to it, it's still next to me. Where's its energy gone, the kinetic energy? It doesn't have any, okay? So what that means is that the kinetic energy, the energy of motion, is observer dependent. Depends who's doing the observing. And it's the same for photons. The energy that you get from a photon is not a property of the photon as such, it's the property of your interaction with that photon. The police use this all the time, right? This is how radar guns work. Okay? The fact that you're moving means that you interact with that photon differently to if you were still. I can see people and okay. We're going to get to the point where I have to tell you that energy is not conserved, and that's when the night really goes downhill.
A question about entropy. They talk about entropy, thermodynamics, and the arrow of time.
Yes.
Entropy. That, to me, seems completely distinct from Einstein's space-time. So is there any relationship between the arrow of time and entropy and space-time?
The answer is yes. You would not be surprised if I tell you it's quite complicated, but okay, so let's do this. Entropy, right? Entropy is this notion of going from order to disorder, okay? So in the universe, what that means is that we're going from useful energy into useless energy. And I can take the sun as an example, right? So the sun, in its core, it's turning hydrogen to helium. That produces high energy, which radiates from the sun. It arrives on the Earth as optical light, which you can think of as condensed energy. and it gets used by plants and us, and we radiate infrared. And infrared is lower energy density. It's lower quality photons, if you want to think about it, okay? So there's this process that's been going on since the start of the universe, where we must have started with very low entropy, and the entropy is increasing because we're going from having lots of order to lots of disorder. And eventually we'll get to a point where there'll be no order left. So the universe is tending towards what's known as maximum entropy, okay? When you reach maximum entropy, where all energy has been processed into the lowest kinds of energy that there is, you don't have an arrow of time anymore. Why? Because there are no processes that can happen. So for us to exist, so for anything to really happen, you need an energy gradient. And for us on Earth, the energy gradient is the sun is hot and space is cold, and we process energy from hot to cold, and we can do that, right? When you get to a point where you can't process anything anymore, there is no notion of time, okay? So, is this tied to expansion? The answer is yes, and in fact, depending on who you would talk to, possibly me. People know the name Roger Penrose? Yeah, you know, Nobel Prize winner from a couple of years ago. He thinks this is the biggest problem in physics, right? Why did our universe start with very low entropy? It could have started with high entropy, i.e. that imagine that our universe was born with all matter locked into black holes. Nothing can ever happen. It's a dead universe effectively, right? So our universe was born in a very strange ordered state that we do not understand. So again, if you're interested, this is called the past hypothesis. And there's lots of people writing about this. But there was something weird about the birth of our universe tied to whatever the initial conditions were, which was what gives us expansion, that allows us to have low entropy at the start that allows us to be here. So yeah, it's a big, messy, confused thing. In fact, all of human life, all of human civilization, everything. If I had this gin and tonic and I plunked some ice in there, we all know what's going to happen, right? The ice is going to melt. Yes? Why doesn't ice miraculously form in the water? Okay? If we were living in a universe which was at maximum entropy, where you just get these fluctuations, every so often ice would form in water, and then other times ice would melt in water, back and forth kind of thing. It doesn't happen. And the fact that my ice melts in my gin and tonic is because the birth of the universe was strange. Think about that next time you have your gin and tonic. And then you can have another one. So
this is the most important question of the night.
okay.
Is any of this useful for predicting the stock market?
The answer is probably.
So two things. Number one, so physics graduates, right? So you probably know this. There's a lot more physics students than there are physics professors, right? So there's not jobs for all physicists. And lots of them go into consulting, banking, trading, etc. Because they have mathematical skills. Now, is this useful? Has anyone heard of Renaissance Technologies? Right? They're on Long Island in Setauket, founded by Simons, who is a mathematician. Okay? Runs the most successful hedge fund in the world. It's been closed for years, still has annual returns of some stupid percentage. Only hires physicists and mathematicians. Can they predict the stock market? Well, I don't know what goes on at Renaissance, but they're not guessing, right? So there's mathematics in there somewhere that they are able to latch onto to get wins. I'm not sure if that's a satisfactory answer, but I wish I was in Renaissance Technologies. See, we're not all useless. There you go.
Okay. What was the?
No. This is right.
What happens to the aircraft carrier entry when it says GTS?
they turned it back on very, very quickly, and they successfully docked in the harbor. That's why we have GPS at the level we do today. So, but again, it might be a completely apocryphal tale. I said I can't remember who told me. Maybe, if you repeat the story, I will kill you kind of story. But I can't remember. But that's what I was told. Yeah.
All right. Well, thanks so much for coming to speak to us the second time. Really fascinating talk. Definitely a lot to think about. I have another gift for you.
Oh.
We gave you one on Saturday night, but we have another one for you. Might not necessarily be useful in Sydney skies, but hopefully you can get out to, at some time you can get out to the country and have a look up in the sky there. But thanks so much for coming to speak to us. Yeah, we've really enjoyed having you here, really enjoyed hosting you, and wish you all the best for your trip back.
Thank you very much. Thank you.
It is actually